Hello everyone. In this video I would like to talk about solving system of linear equations, and in particular we will see Gaussian elimination method. Let's get started. This is a linear system of equations. First of all, what's a linear equation? We should understand. In the first example here, the equation given, we have all the terms with respect to x1, x2, and x3. All these powers are just 1, as you see. So this is a linear equation. So if we have only linear terms with respect to the unknown variables, we call this as a linear equation. But if we have some nonlinear terms, such as the cross multiplication of two variables like x1 and x3, then this becomes a nonlinear equation. Similarly, if we have some powers such as the cubic power or square, the fourth order or square root terms, anything basically that doesn't have the power equals to 1, then this will become not a linear equation, a nonlinear equation as we call it. So when we have a system, basically we will be talking about n number of variables, and we will be given m number of equations. So each equation is a linear equation with constant coefficients. Then this is the linear system of equation that we are going to solve in this video. So if the system has a solution, it is called consistent. Otherwise, it is going to be called as inconsistent. And also note that if the right-hand side of each equation is equal to 0 for all these equations, then we call this as a homogeneous system if this condition is satisfied. And if we have a homogeneous system, basically we always have at least the trivial solution. The trivial solution means just plug in all x values equal to 0, and that's going to satisfy our system. So at least we have the trivial solution if we have a homogeneous system. Now we will talk about the Gaussian elimination method in particular. And in order to apply the Gaussian elimination method, we need to go over some very basic matrix algebra operations as well. First of all, this is our matrix m by n, and we represent this matrix with these entries a1, 1 all the way to a1, m. This is our matrix A. We have these coefficients represented as a1, 1, a1, 2, and a1, n. And the rows, we have m number of rows. So this is indicating the number of rows and the number of columns. So this is an this is an m by n matrix, and we can represent each element in this matrix as aij, where I is from 1 to n and j is from 1 to m. So this is just our general notation to represent a matrix. Now with matrices we also can do various operations, including summation, subtraction, multiplication, etc. First of all, we need to go over the definitions of these matrix operations very quickly. So here are the matrix operations. A equals to aij, which is assumed to be an m by n matrix, and suppose B is given as these bij terms with n by m matrix as well. So if the dimensions of these two matrices match with each other, they have the same number of rows and same number of columns, then we can do a summation of these two matrices. And the summation will be done by summing each aij with the corresponding bij element. And after we do this element by element, we will get the sum of these two matrices. Let's look at some examples. Suppose we are given a matrix A, which is 2 by 3, and we are given also another matrix B, which is also 2 by 3. So the dimensions agree, therefore we can do the summation. And in the summation, we will sum A11 with B11, that is 3 plus 4, and you write the 7 here. And then move on to the next element, 0 plus minus 3, you get minus 3. Minus 1 plus 6, you get 5, and so on. So that gives us the summation of these two matrices. Next, we should explain what's the multiplication with a scalar for a matrix. So again, we are representing our matrix A using Aij, where I and j are the row and column index of each element. And suppose you want to multiply this matrix with a scalar, which is C, a real number. So multiplying with C times A, that means every element in this matrix will be multiplied with the same scalar C. Here's an example. If I'm given a matrix A, and if I want to multiply this with the scalar minus 2, each element, minus 1 times minus 2, we get minus 2, minus 1 times minus 2, we have 2, minus 4, and minus 8. So here is the multiplication with a scalar. Similarly, you can continue with subtraction and multiplication. Basically, subtraction, there is nothing interesting for us because you can think of subtraction as summation, which is we have already did with an example. So instead of creating another example for subtraction, you can just think it as summation, but with A plus minus B. Next, let's talk about multiplication. Now, if you want to multiply two matrices, the dimensions of these two matrices should be suitable for multiplication. And what we mean by that is the number of columns in the first matrix should be equal to the number of rows in the second matrix. So if the matrix A has the dimensions m by p, and if matrix B has the dimensions p by n, these are the same, therefore we can do the multiplication. Let's see an example. The multiplication of A times B equals to C, so this will be an m by n matrix as a result of this multiplication. And here is how we do the multiplication. If I'm multiplying two matrices A and B, I will multiply the first row of A with the first column of B, and that will be my C11. And then I will move on to the second column. I will multiply the first row with the second column here, that is given with these elements. So that will be written as my C12. And then I will move on all the way until the last column. So I will multiply the first row with the last column of the second matrix, and that's going to give me C1n. And then you will move on to the second row, multiply with the columns of the second matrix, and fill these C21, C22, and C2n values. And you need to continue these row by row all the way until you complete the m number of rows. So the multiplication of these two matrices, we can also write this in a summation form using the elements Aik times Bkj that are coming from matrix A and matrix B. So this is just an alternative representation of what we have explained in these row and column multiplication and summation of these terms, and we are writing these as the elements of matrix C. Let's look at an example. Suppose I'm given matrix A, and I want to multiply this with my matrix B. Both of them are 2 by 2, so there is no problem in terms of the dimensions. And if you do that, you will multiply the first row with the first column. So 2 times 1 and minus 1 times 3, so you get 2 minus 3. And then 2 times 5 minus 1 times 7, so you get 10 minus 7. And then for the second row, now you need to multiply minus 4, 3 times 1 and 3, so you get minus 4 times 1, and then 3 times 3, that's 9, and then just continue in this manner, so you will get the result as minus 1, 3, 5, and 1. Now, we should note that a times b is not equal to b times a. So we can see that there is no such property by considering b times a. So if you multiply b and a, you are going to get a completely different result. Now, two matrices are called as equal to each other if every element is equal to each other, or in other words, they are identical in terms of the element corresponding in the same indices. So for all ij, aij values must be equal to bij values for I from 1 to m and j from 1 to n. Here's an example. Suppose we are given matrix A. So we have a 2 by 3 matrix A, and then we are given another matrix B, which is also 2 by 3. So we have some unknown parameters here. If these two matrices are equal to each other, we can easily identify these parameters. For example, this will correspond to the value t, and then we have minus 1, which must be the case because these two matrices are equal, so every element-wise, they must match. And then we have minus 5 here, that should match with this x. And then we have 3, 3, and then y must be equal to 0. And again, we have 12, 12 here. So if these two matrices are equal to each other, then we should have x equals to minus 5, y equals to 0, and t equals to 2. Here's another example. Now we have a system of two equations and two unknown variables, x1 and x2. Now, how can we represent this system in matrix notation? So remember, first you need to write these coefficients as the coefficient matrix here. So the coefficients of x1 and x2, the first coefficient here is minus 2, and then the coefficient of x2 is 3. Then you should move on to the second equation, x1, so the coefficient here is actually just 1 times x1, so you just write down 1, and then we have minus 6, and we write it down here. And then the right-hand side is minus 6 and 3, so we should put it as the right-hand side of this equation. So as you see, since we know how to do multiplication, you can get back the equation itself. Because this is the first row, it will be multiplied with the first column, so you will have minus 2x1 plus 3 times x2, which is the first equation. And then if I multiply the second row with the column here, that's going to give me this second equation here. Another example, we have again a system of equations, a 2 by 2 system, two unknowns and two equations. We have 5x1 minus 2x2 equals to 3. So what you need to do is again represent this using the matrix multiplication. So instead of writing these equations, we can write down the coefficient matrix, which is the coefficients here 5 minus 2, and here we have 0 times x1 actually, so that's why we have 0. Actually you can write this as 0 times x1, so the first coefficient here is 0, and then we have 4, and basically here we have the unknown variables x1 and x2, and on the right hand side we have this vector 3 and 10. Now, since our goal is to use the Gaussian elimination method, we need to introduce one definition here, which is the augmented matrix. Actually, augmented matrix is a simple notation of representing the coefficient matrix together with the right-hand side of the system. So, instead of writing these separately, we can just write down A augmented with B, which means we have this coefficient matrix, and then the right-hand side of the system that we are trying to solve is given by these elements from B1 to Bm. So for example, A augmented B. So you have this coefficient matrix, and then the right hand side values are minus 6 and 3. In other words, this is equivalent to a system. So this is equivalent with representing a system, basically minus 2 times x1 plus 3 times x2 equals to minus 6 as the first value on the right hand side. And then we have x1 times 1 minus 6 times x2 equal to 3. So instead of writing these equations one by one, we can directly use the augmented matrix to represent this problem. Now we should talk about the echelon form, which we will be using in the Gaussian elimination technique in order to get the solution of the system. And here we can see some examples. In the echelon form, as you see the first example, we have the leading term equals to 1. And then below that, in the second row, we should not have any other non-zero term. So it must be equal to 0. So the below this leading term 1, all the elements below must be equal to 0. And then when we go to the second row, as you see, we have this term. This is also 0. And then we have a non-zero term, that is 2. And then the terms below this term that follows in the third and fourth rows, they must be equal to 0 as well. Similarly, in the second example, you see we have 1, 2, 0, etc. So the first row, we have the leading term equals to 1. And then below that, we have all these 0 terms. And then for the second row, as you see here, the leading term equals to 1. And then below that, in the third and fourth rows, we have zeros. And then we have the one non-zero term is here. And then below that, again, we have 0 in the last fourth row. So this is in the echelon form. This is also in the echelon form. As you see, this is also in the echelon form because, as you see, we have zeros, and then we have a non-zero term, and below that, again, we have 0. And similarly, this is actually the identity matrix. Identity matrix is also in the echelon form. So that's also a valid form. Now, what about not in echelon form examples? What might be the counterexample? First, for example, I have the leading term equals to 1. And then in the second row, okay, these are 0, that's fine. And then in the second row, I have all the terms 0, but the third row, I suddenly have a non-zero value here. So this is not in the echelon form. Actually, I need to put this third row into the place of the second row if I want to convert this into the echelon form. But as it is right like this, it is not in the echelon form. Another example, the leading term here is 0, but then below that we have a non-zero term. Again, this is not in the echelon form. Another example, you have 1, 2, 3, and then below this leading term 1, we have a 0 here, and then minus 1 here. But below this 0, we have a non-zero term. So this basically gives us the counterexample, because this must be 0 if we want to put this in the echelon form, but it is not. So it is not in the echelon form. Now, let's look at this example where we are given a system of equations. We have 3 equations, but we have 1, 2, 3, 4, 5 unknown variables. So in this example, the number of unknown variables is more than the number of equations. So if we put this system into the echelon form, what do we have? We have 1, minus 2, just write down the coefficients first. So that's our augmented matrix actually. And then write down the right-hand side of each equation. And this is already it is already in the echelon form. So we have the third equation, for example, x4 minus 4 times x5, that's equal to 7. So basically, this system cannot be solved. Back to this augmented matrix, actually we have infinitely many solutions because, as we have seen, the number of unknowns is more than the number of equations. So in order to complete this system, we use parametrization. Parametrization helps us to complete the system by introducing actually extra equations with respect to some scalars that are unknown. For example, in order to complete this system, I need to introduce two more equations. So I can let x2 to be represented with the parameter r, and I can let x5 to be represented with the parameter t. Then we can write the rest of the variables in terms of r and t. So the other variables, x4, we know that x4 equals to 7 plus 4 times x5, and x5 is equal to t. So this becomes 7 plus 4 times t. And similarly, you can move on to x3, and then x3 equals to minus 3 minus 2 times x5. So this is x5 is equals to t. So this becomes minus 3 minus 2 times t. And then move on to x1. And just by substituting all these values, you can write down x1 in terms of these parameters r and t. But effectively, r and t are arbitrary parameters, so we have infinitely many solutions to this system. We have this time 3 equations and 3 unknowns. And we start by writing this. We have the coefficient matrix, we have the right-hand sides. So this is the so-called augmented matrix here. And then we can do some row operations. So that's the essence of Gaussian elimination method. We use row operations in order to get the echelon form. And once we get the echelon form, then the solution will follow. For example, here, this is our coefficient matrix that we started. So my goal is to put this in the echelon form. So I need to eliminate these guys. I need to convert them into zeros by doing some row operations. Because doing row operations doesn't actually change this system. It is still the same system, but for example, think about I multiply the first equation with minus 2, and then I can add to the third equation to cancel this guy. Or I can multiply the first equation with minus 3 and then add to the second one to cancel this guy. So that's the goal. I mean, we are not changing anything in the system, but we are representing it in an equivalent representation that will help us basically to get a more convenient representation. So for example, here, as we said, we can multiply the first equation with minus 3 and then add to the second equation. This will become 0, right? That's going to be minus 3 times the first row, and then add to the second row. This will become 0. This is 2, 4, and 8. Now multiply the first row with minus 2 and add to the third row. So with minus 2 and then add to the third one, you get another 0 here. And then you get 7 minus 4, that's 3. And then 9 minus 2, that's 7. And then 23 minus 8, that gives you 15. As a result of these two operations, row operations, we can get this matrix now. Now, what's the goal? I need to have also this element here 0, because I want the echelon form, as we mentioned. But before that, we can simplify the second row a little bit. Notice that I can divide every element, every coefficient by 2. It doesn't change anything. So I can write this as 1, 2, and 4. And then I rewrite my third row. Now, I can multiply my second row with minus 3 and add to the third one, so that I can get a 0 here. So we have minus 6, 7 minus 6, that's 1. And then we have 15 minus 12, that's 3. So now everything is in the echelon form. 1 times x3 equals to 3 from the third row here. From this third row we can write it. And then from the second row you see x2 plus 2 times x3 equals to 4. And then from the first row you can write x1 plus 2x2 plus x3 equals to 4. Now we already know that x3 equals to 3, and then I can find x2, and then I can find x1. So this is why echelon form is really useful for us, because once we get it, the last unknown variable is obtained directly. Another example, I have 5 unknown variables and 3 equations. So by looking to this problem, we can see that we have too many unknowns compared to the number of equations. So we will get infinitely many solutions in this problem, and we can do some parametrization in order to get these, or to represent these infinitely many solutions. But how you will approach this problem is exactly the same. First, you need to write down the coefficient matrix, and then the right-hand side values. So this is the augmented matrix representation. And then start doing some row operations in order to get the echelon form. For example, you can multiply the first equation with minus 2 and then add to the second one to get this 0. So if you multiply with minus 2 and add here, this is also 0. And this is 2. And then you have minus 1, because 3 minus 4, that's minus 1. And then you have 10 minus 2, that's 8. And then the right-hand side here is minus 13. Similarly, multiply the first equation with minus 3 and then add to the third one to get this 0. And also notice this will also become 0. And then 10 minus 9, that's 1 here. This is also 0, 2, and minus 3, because minus 30 plus 27, that's minus 3. Now we are getting close. Actually, I can swap the second and third rows, because I get this 1 here. So I would prefer to put this as my second row, as you see. And then I can multiply the second row with minus 2 and add to the last one. So that will give us, that will cancel this 2 here, that will become 0. This is still minus 1. And 8 minus 4, that is 4. And then we have minus 13 plus 6, we have minus 7. And if you like, you can also multiply this with a negative sign. So this will also become, the last term here will become plus 1, minus 4, and then the right-hand side will become plus 7, if we just adjust with this minus 1. And then it's going to be in the echelon form. That's what we wanted. Then what we need to do is to parameterize, to use the parameterization, because we have more unknowns than the number of equations. So I need to complete the system by introducing these arbitrary parameters. So let's say x2 equals to s and x5 equals to t. Okay, these are arbitrary real numbers. So we can do that. And then once we assign these unknown parameters, the rest of the variables also follows. So if x5 equals to t here, you can solve for x4 as 7 plus 4t. This is the parameterization. And then what about x3? x3 equals to minus 3 plus, minus 3 minus 2 times x5, but x5 is just t. So that gives you x3. We already parameterize x2 as s. And finally, x1 is, you can solve for x1 here. You have 10 minus x5 minus 2 times x4 minus 3 times x3 and plus 2 times x2. So that gives us 5 plus 2s minus 3t. And then we can finally represent this solution for x in terms of these parameters s and t. Let's look at to the next example. We have three unknowns, x1 and x2 and x3, and three equations. As usual, start with the augmented matrix and try to achieve the echelon form in order to get the solution. So here is this is my coefficient matrix and the right hand side. So this is the augmented matrix. So I just write down the coefficients. And then we need to do some row operations in order to get these terms equal to 0. So first, we can do a swap because I already have 1 here. So I want the first row to be this guy. So I take it as my first row. Then this is the first row. And then I have 3, 1, and minus 3 as my second row actually. But I can multiply the first row. I can multiply my first row with minus 3 and add to the first one. So if I multiply actually this guy with minus 3 and add to this guy, that's going to cancel this equal to be 0. And then minus 3 plus 1, that's minus 2. And then minus 3 minus 3, that's minus 6. And then minus 3 minus 4, that's minus 7. And then I have 5, 6, and 8. But we can also take care of that. If we multiply these guys with a minus 5, and add to this third row, then you get 0. And then you have minus 5, 6 minus 5, that's 1. And then we have 8 minus 5, that's equal to 3. And then we have 8 minus 5, again, that's equal to 3. So now we are getting close. But now I can actually simplify this guy, and I can put it in the third row. So first we can take this third row as the second row, and the second row becomes the third row, so that this is equal to 1. But I can also simplify this second row by dividing with 2, so this becomes 1, 3, and 7 over 2. But now, as you see, these are the same, but the right-hand sides are different. So this is a contradiction. If we get a contradiction, that means no solution for this system. Let's look at to the next example. We are given a 3 by 3 system, 3 equations, 3 unknowns. As usual, start by the augmented matrix here. You have A augmented with B. Write down the coefficients and right-hand side. And then start to do some row operations until you achieve the echelon form. And we need to get these, below the leading terms, we should get the zeros here. And you can notice that we have 2, 1, 3 here. And we have the third row starting with 1. So I can swap the first and the third rows with each other. So now this is my first row, and then this is my third row. And now I can start to do my operations. I can actually multiply the first row with minus 2 and I can add this to the, if I multiply this with minus 2 and add to the last row, that's going to be 0. do the swap, we can add the first row. Actually, that's originally the third row, but I'm adding to this guy. So 1 minus 1, I will write it here 0. And then I have 2 plus 1, that's 3. And then minus 2 plus 1, that's minus 1. And then minus 1. And I have 2, 1, 3, that's because of the swap. So because of the swap, we interchange these rows, which doesn't matter. I mean, for example, in this system, think about changing the last equation, write it as the first equation. Does it matter? No, it doesn't matter. And then our goal is also to get this guy equal to 0. So I multiply the first row with minus 2 and add to the third one. So I get this 0, minus 3, 1, 1. Now, my system starts to become simpler. It's becoming simpler. As you see now, I can add the second row to the third one. So this will become 0, 0, and 0. And also you can simplify the second row by dividing with these 3. If you divide everything by 3, then this is also becoming simpler. And you can rewrite this now as the first row gives me this equation. The second row gives me x2 minus x3 over 3 equals to 1 over 3. Then, because the third equation is not giving me any information, it's just a true statement, 0 equals to 0 is always true. So effectively I have 2 equations here and 3 unknowns, which means I have infinitely many solutions. And in order to represent these infinitely many solutions, we do a parameterization. We let x3 equals to r, and then x2 and x1 can be obtained as minus 1 over 3 plus r over 3, and x1 equals to 2 over 3 minus 5r over 3. So that gives us the representation for the infinitely many solutions. Let's look at to the next example. This example is slightly different. Now, it has already some unknowns in this given in these system of equations, and it's asking us what should be lambda and beta for no solution case, infinitely many solutions, or unique solution. For each case, we should think about what should be the value for lambda and beta so that we get one of these cases. And we can start as usual, writing down our augmented matrix as usual, and then start to do some row operations until we get the echelon form. So this is the augmented matrix. Now remember, we should get some zeros below the element here. So you can multiply the first row with minus 1 and add to the second one. That becomes minus 4 plus 3 minus 1, 2, 2 minus 1, that's 1, and then beta minus 2. And then we have to similarly do the similar operation for the third row to get this 0, and then 4, and then lambda plus 1 minus 1, that's just lambda, and then 6 minus 2, that's 4. Now we are getting close, but we should also make this guy 0. So I can multiply the second row by 4 and then add to the third one. So I get this 0, and then lambda plus 4, and then 4 times beta minus 8 plus 4, 4 times beta minus 4. Now, let's think about, for example, what if this is equal to 0, and if this is also equal to 0, what happens? If both lambda plus 4 equals to 0, which means lambda equals to minus 4, and if 4 beta minus 4 is also 0, which is beta equals to 1, then that will give me infinitely many solutions because the last equation effectively will be useless for us. It doesn't give any information. So I have 2 equations and 3 unknowns in this case. And that's the infinitely many solutions. But what about if the left-hand side is 0, but the right-hand side is not 0? Well, that's a contradiction, as you know. I mean, if we have 0 is equal to, let's say, 5 or 10, whatever, then that's a contradiction and we cannot find any solution. That's the no solution case. And then what else can we have? We can have a non-zero lambda plus 4, so lambda is not equal to minus 4. Then beta can be any real number because we can uniquely solve this system. So that's the unique solution case. Next example, we are given a 2 by 2 system. We have an unknown parameter k in this system. So as usual, start writing your augmented matrix. Try to put it in the echelon form using the row operations. And this is my augmented matrix. And notice that here the right-hand side is 0. It's a homogeneous system. And we have 3 to 6k. And I can multiply the first row with minus 2 and add to the last row. So this will become 0 here. And then I will have k minus 4. And the right-hand side is also 0. So if that means if this is equal to 0, the right-hand side is also 0. So if k equals to 4, then I just have effectively one equation in this problem. X plus 2 over 3y equals to 0 from the first here. So from the first problem, from the first row, we have 3x plus 2 times y equals to 0. But you can divide everything by 3, just if you want to write this in this form. That corresponds to our first row in this augmented matrix. So that means if k equals to 4, I'm going to have infinitely many solutions in this case. So we have infinitely many solutions, but we can represent these solutions with respect to the parameterization y equals to r. If y equals to r, if I let this to be my parameterization, then my x is written as minus 2r over 3, which is the infinitely many solutions. And if k is not equal to 4, then we will have only the trivial solution, because if k is not equal to 4, this will give us a contradiction here, so we cannot get any solution from here. But because it's a homogeneous system, I will have only the trivial solution in the case if k is not equal to 4. Next example, we still have one unknown parameter k. We have 2 equations, 2 unknowns x and y. So start with the augmented matrix 3, 2, 6, 4, and you can multiply the first row with minus 2 and then add to the second one to get these equal to 0 and k minus 2. Now notice that if this is 0, if this is also 0, I have infinitely many solutions. So if this is the case, infinitely many solutions. If k minus 2 is not 0, then that gives me a contradiction. So no solution for this system. So we completed our examples about solving linear systems of equations using the Gaussian elimination method. Thank you for watching.